Greetings from astronomers. Our aim is to utilize artificial intelligence to solve the problems in modern cosmology. Now, let us walk you through some background and motivation for choosing this project. Studying large structures is an active research area, and large-scale surveys are the future of modern cosmology. There are many areas to explore, but our main focus is to find galactic redshifts. Galaxies that are far apart from us and constantly moving away with acceleration appear to be more redder than they actually are, and this phenomena is known as redshifts. Now, we know what redshifts are, but how do we measure them? The answer lies in the type of data we are getting from the sky. Traditional methods of finding redshifts rely on spectroscopy. Spectroscopy is the study of interaction between electromagnetic radiation and matter as a function of wavelength and frequency. The features used in spectroscopic surveys are spectral energy distribution, dust attenuation, and nebular emission lines. Redshifts measured from these surveys are called spectroscopic redshifts. Now, this is a very good way to measure redshifts accurately, especially when we are looking at relatively small scales. But it becomes a problem when we move to large-scale surveys. Since it depends on methods like template fitting and other iterative approaches, it becomes very time-consuming and expensive. The other possible way to get redshifts is using photometric data. Photometry is the study of brightness of light observed through various filters. The redshifts obtained by this survey are called photometric redshifts in literature. So now let's try to understand the data that we are getting. So the photometric data contains 5 channels. More specifically, the data that we are using contains 5 channels and consist of ultraviolet, green, red, infrared, and value for brightness. It is collectively called as Euclid's band. So just to compare with a normal image, this is how a normal RGB image with 3 channels looks like. So we have one channel for R, one for G, and one for B, and we just stack together to make this RGB image. Now this is the data we got from SDSS, and it contains 5 channels U, G, R, I, Z, and these are just how we view them separately. So now after going through a lot of pre-processing and using some Linux-based tools to specifically pre-process on astronomical data, we finally got our data, which is the photometric data. And now the problem is that unlike spectroscopy, we don't have a direct function or a direct map that can take us from photometric data to redshift. More specifically, we will call it photometric redshifts. So this is the question mark, and this is the problem that we will try to solve. The solution to this problem is to use spectroscopic redshifts as true values and train a deep learning algorithm which will take photometric data as input and predict redshift. And we will treat, since we already have a lot of data for spectroscopic redshifts, we can treat them as true labels, and then we can train our algorithm. This is the purpose of this project. We will be developing a deep convolutional neural network, which will help us to predict photometric redshifts. So now let's talk about the experiments that we performed. First of all, we used state-of-the-art architectures to test what we have. And we applied these different networks. Our main focus was on a modified version of GoogleNet. And as we can see that GoogleNet and ResNet 50 were overfitting the data. Meanwhile, VGG19 and ResNet 18 weren't actually able to learn the distribution. The basic criteria that we use to evaluate our model are following. So first of all, we plotted residuals, because residuals are very important when we are talking about this astronomical data. And we need to know how much error our model is making, because that's very important when you are using a model in surveys. And then prediction bias is just the mean of residuals. Median absolute deviation, again, it's dependent on residuals. And finally, we have this metric called number of outliers, where we just select a particular number of error that we can tolerate, and every data point which gives us more than that error, we will term it as an outlier. So after that, we also proposed our own architecture, which is right now in its final stages of development, and then we will test it. So this idea is actually inspired from GoogleNet. So what happens in GoogleNet is there is a block called inception block, in which we try different filters of different sizes. So let's suppose I have 3 by 3, 5 by 5, and 7 by 7 filter. And then at the end, we just add them. We just concatenate them. So our criticism is that we should not give equal weightage to all the filter sizes, and we should add some kind of weightage. So that's how the idea was born. And then we applied this weighted convolution block, in which we will also learn the weights of different filter sizes, and then we will this will continue in the learning process. We also visualize the layers of our architecture, and these are the results of visualization on the layers of a modified version of GoogleNet. So this was the result after applying first convolutional layer, and we can see that it's kind of focusing or blurring on the galaxies. This is the result after some more layers and going deeper, and either it's like focusing or blurring the galaxies, or like distorting everything from the borders. And this is again after some more layers, and we can see now we cannot actually make much sense of it. So to be honest, this visualization does not really help us to make our architecture better, but yeah, we were just able to sneak peek in about what is happening. Now let's look at our working prototype. And this is a prototype we are developing a command line interface because our target audience are the researchers who will be using this models or the future surveys that will need this model to get the redshifts. So here we are just testing some commands like we did get MPY and we get. And again, like another command we tested is get RGB composite, and here we will just provide 3 files instead of 5 files because we just need RG and B. And we can see that it will again make a file of RGB. Thank you so much for watching. Hope you enjoyed this video.